Good morning. Welcome to my webinar on strategic supply chain network design, a practical approach. The second slide shows my resume, so I don't want to repeat that. You can have a look at a later stage also. And in fact, I spend most of my time in industries, and I did my PhD from IIT Madras after my retirement. So these are some of the projects I have taken up, and I was teaching for the last 12 years in various institutions, management institutes in India. In fact, I would like to narrate a story which happened when I went for admission in IIT Madras. And the head of the department who took my interview along with a lot of other professors, so everybody has finished their part, and then HOD asked me a simple question at the end that, Bhattacharya, could you tell us in one sentence, what do you mean by supply chain management? We are going to do research on supply chain management. I was a little bit perplexed, and to tell everything in one sentence was a tough job. So anyway, I looked up and then I replied. What I replied is given below: supply chain management. Now, if you change supply and management, these two words, you just interchange. What do you get? Management, chain, and supply. Now you put two prepositions of in between this. What do you get? Management of chain of supply. I told my head of the department that supply chain management is nothing but the management of chain of supply, right from suppliers to the customers. HOD said that you are through. That is how I entered IIT Madras. Gentlemen, in fact, this chain of supply comprises a series of networks, right from suppliers to customers. When you receive the materials, you have a network. When you move the materials or products or semi-finished goods inside your plant, there is a network. And when you distribute your final product, there is a network. Now, today's lecture, I'll be concentrating on the distribution networks for the final products. So let us see what is the objective of doing this network design. I have written one by one. I'll have to select the right number of facilities, location of the facilities, size of the plants or warehouses. Secondly, territories each plant would serve. No unique solution. World is very complex. It means that however hard you think, you will not be able to get an optimum solution from the problem you try to solve. In fact, there is no unique solution because of the complexity of the constraints. Then you construct a logical mathematical model and solve the same with the help of powerful optimization tools. Now, ultimately, you arrive at the most satisfying solution out of many possible outcomes. In fact, I always use most satisfying solution instead of an optimum solution. So basic building blocks, a supply chain, you all know about it. It comprises of suppliers, plants, warehouses, flow of products from each other's region to the final customers. In fact, you please remember 80% of the cost of supply chain is locked up in the location of the facilities and the optimal flow of products or parts between them. Most successful companies in the world place tremendous emphasis on determining the best locations, size of these facilities, and the best flow of products through this. Now, once you go to the network design, you should be able to answer some of the questions which management might ask you. How many warehouses should we have? Where should they be? How large they should be? And what products should they distribute? And how would we serve our customers? So one side, I'll have to serve the customers, and another side, I'll have to reach the customers as fast as possible. Secondly, how many manufacturing sites should we have? Where should they be? How large should they be? How many production lines should we have? And what products should they make and which warehouses they should serve? Thirdly, you must know what products we are making internally and what we are offshoring or outsourcing. If we outsource, then which suppliers should we use? Now, once you are able to answer these questions, then let us look at some of the distribution strategies which are in vogue in many organizations around the world. This is nothing but direct shipping. Here, the material flows from A to X or Y or Z, and then the full truck comes back. From B also, it goes to X, Y, Z, and from C also X, Y, Z. So these are generally used for products with high volume and low demand uncertainty, and there is an economic of scale in the operations. It's full truckload shipments, and this provide good customer experience, and postponement can be carried out. Now, this customers, if they have a high volume and there is uncertainty in the demand, only this is applicable. Now, there is another method which is called milk run system. We have been using these systems for either for bringing the materials from the suppliers, or sometimes it is used for delivering the final products. Here, for example, A delivers the material to X, part delivered, and then it goes to Y, and then delivers the balanced parts, and then go to Z, final balanced parts, and then it goes back to A. So here, aggregation of the product-wise demand across all three depots. Now, there are 3 tips compared to 9 tips which we followed for the direct shipment. And depots get more often served, and hence more transportation cost. Lower cycle inventory, because I'm giving small quantities, so cycle inventory is Q by 2, whatever I'm supplying, that divided by 2 is the cycle inventory. And works well when all depots are located in close proximity. So here, these are located very in close proximity, and so naturally they are served by this system. There may be another system, manufacturer storage in transit merge network. So there are warehouses or retailers they merge the components and then supplies. Examples: Dell and Sony assemble PC, monitor from one source and keyboard from other, merges together at the hub. So in this hub, they combine all these materials and deliver it to the customer. So the dotted line gives the information flow, and product flow is shown by the form lines. Distribution storage with the last mile delivery. Here, from factories, materials, products goes to distributor or retailer warehouses, and then from there, it goes to the customers. So these are generally used for home delivery, distributor warehouse closer to the customer. Manufacturer or distributor storage with customer pickup. I need not explain. See, you must be going to MUL or any other place where you just go and pick up your materials. So in between, there are cross-dock facilities or retailer is there. So they, from the cross-dock facilities, some materials goes directly to the pickup sites, or it may be stored in some of the warehouses and then it goes to the pickup sites. Now, with this idea of the distribution, there are many other strategies, but I showed you some of them. And there is a hub and spoke mechanism also for distribution. Materials are collected at the central hub, and then from there it distributed all around. I think Mr. Bhatta has explained to you yesterday. And this, once you understand this strategy, now your network design project should be able to answer some more questions. What is the trade-off between number of facilities and overall costs? You must understand that if you increase the number of facilities, then that means you are incurring more cost. So are you in a position to spend so much of money by putting additional facilities? Then what is the trade-off between service levels and number of facilities? If you want to serve the customers well or more than what the present level, then you'll have to increase the number of facilities. But is it justified? Similarly, what is the impact of changes in demand? Suddenly your demand goes down or goes up. Labor cost goes down or goes up. Then commodity pricing changes. Then will your network work or the configuration will change? Now, those things you must be able to answer with your design. When should you make the products to manage seasonality? So if there is a seasonality of demand, then naturally the demand will fluctuate, and then are you in a position to handle that? So how do you ensure capacity and flexibility within network? That means whether you will add new or old plants, when to add capacity, etc. Now, how do you reduce supply chain costs? And so coming back to some of the graphs which has been plotted for various organizations around the world. Now, if you want to reduce the response time, you must increase the number of facilities, it shows. If you increase the number of facilities, facility cost naturally will go up. Inventory cost goes up as you increase the number of facilities, but remember, it reaches a plateau after some time. Then transportation cost and number of facilities, transportation cost goes down as we increase the number of facilities, but again, it goes up. So total cost is how it is related to facility cost, inventory cost, and transportation cost, this graph shows. Then the modern supply chain, most of them are located worldwide. So geography actually drives your transportation cost, then service levels, risks as you spread beyond your country. So naturally more risks are involved. And then taxes, carbon emissions, all these things comes into the picture. Now, reasons for warehouses: consolidation of products, buffer lead time, service levels, production lot sizes, inventory pre-build. So these are the various reasons. Then transportation mode trade-offs. Types of warehouses, it may be cross-dock, plant attached to warehouses, hub or central warehouses. Why multiple plants? Because you want to serve your customers better. Then transportation costs, you want to reduce. Then economies of scales. Then taxes, then steps in production process. Sometimes you have multiple plants. One plant makes the materials, and then another makes the assemblies. Then plants representing many types of facilities. It may be a manufacturing or assembly site, a supplier, third-party manufacturer. Solving the problem. So now you have a problem in your hand. So we'll start the small problem and show how it goes. So any problem, you must have an objective function, you must have some constraints, and you must have some decision variables, and then over and above, you must have data. Without data, you cannot solve problems, so you must have the data. Two specific uncertain, I put another one. So three specific uncertain elements are there when you design a network design. One is the demand. Demand may fluctuate from time to time. Transportation cost, it may also fluctuate. Transporters will never keep the rates constant, it may vary. And then production cost may also vary. So the product which you are picking from some sources, their price has gone up, or you in your facilities you must have utilized some other automated machine, so naturally your cost has gone up. So these are the elements which you have to take into consideration before you go through sensitivity analysis. So characteristics of data. Data collection is very, very important in network design. Now define the data needed with the right level of significance. So the data which are not significant, there is no point in dealing with them. Every piece of data should not be very accurate up to say 3 decimal points. There is no use. You must have a data which even you can aggregate those data and utilize those aggregated data. The result will not be much different from if you utilize up to 3 decimal places, or if you take all customers into account. There are various methods of aggregation, which I'm not going into detail. So it may be weight-wise, it may be packing-wise, it may be size-wise. So like that, it may be even pin code-wise, you can aggregate your customers. Customer you can aggregate. So now let us come to the practical center of gravity models, which we are going to describe instead of center of area or center of gravity model. Now problem background, there is a big country. Now we call it Logistica, okay? Now the citizens are looking for a place for their capital. Now, in our country, capital is Delhi. So everybody wants to go to a place close to the seat of government. But is it feasible or possible? Watch this analysis. Logistica. So this is a country, it's in the United States, you can say. And these are the cities all around. 1, 2, 3, 4, the serial number is given. Now, where do you locate? The planners want to decide to place the capital in the central position. So first they want to locate it by considering the boundaries. So they want to consider the boundaries of Logistica and select their capital. Now you have the data, you have the latitude and longitude for all the cities, and their populations are also here. And distance you can do like this. This is the formula used for distance if longitude and latitude are given. Otherwise, you can take the plane distance. So now if you calculate the average distance a citizen has to travel to reach the capital, it comes to 471 miles. So how it is calculated, I'll show you like this. So you have found out the center of the area, located here, the red square, and you use this formula. That means population of each city multiplied by distance is X. So you can multiply this and sum it up and divide it by the total population. If you do it, you will get 471. So 471 is the average mile a person has to travel to reach the capital. Am I clear? Now, some planners, what they thought, will go to their friends of physics, and they decided that we'll locate the center of gravity, use the center of gravity method to locate the capital and find out whether there is a benefit or not. So center of gravity, you can find out the coordinates of the capital by using this formula. And they found out it comes to this place shown by a red rectangle, and which has gone right from the center of area because of the fact that most of the demands are located around this place. So it is a weighted demand method, so naturally it has shifted to the right. And the result is this, although we have found out the capital and the center of gravity method by using center of gravity method, but this falls in a shark infested water offshore from a mountainous and deserted region. But hence the people would not be happy to go to that place and for doing their job. And infrastructure wise also that is not suitable. Although there is an improvement in the average distance a person has to travel, it is an improvement by 83 miles, because now it has come 388, previously it was 471. So, but it proves impractical and hence not accepted. So physics center of gravity method cannot be used. It does not minimize what we want to minimize. It might point to a place in the middle of the sea or on top of mountains or middle of desert. So it cannot be extended to take care of different products, costs, multiple level of facilities, etc. And it cannot take advantage of true road distance. So let us take a small example, linear example, to make it a problem, a much simpler problem. Suppose we have two cities, Portland and Eugene. So they are 100 miles apart. Now, Portland has a population 9 million and Eugene has a population of 4 million. Suppose I want to locate the capital, where should I locate it? So if I locate it at a distance of x, then the other distance is 100 minus x. So suppose I put it at x equal to 0, let it be at Portland, then total person miles is 9 million into x plus 4 million into 100 minus x. So if you calculate and divide it by total population, that is 13 million, 9 plus 4, what will happen? I'll get on an average 31 miles. If x is 50, then it moves up to 50 miles. If x is 100, it moves to 69 miles. Hence, minimum person mile is 31, and hence capital should it not be located at Portland? Because I get the maximum advantage out of this, and people will have to travel less on an average. So this is what is called practical center of gravity method, and calculation is done by total personal miles. Now let us look back to the center of gravity which our friends in physics suggested. What they suggested, that you use this formula and put the capital at 31 miles from Portland. But if you put it Portland at 31 miles, you will get 43 miles per person, which is worse than 31 miles. So should you use 43 miles? No. So the calculation is given here for your benefit. 9 into 31 plus 4 into 100 minus 31 equal to 43. So what is being minimized in center of gravity method? Suppose we take an equation like this, S equal to 9 million into x minus 0 whole square and 4 million into 100 minus x whole square. You take the derivative of this, So you take del S by del X. So if you do like this, then you will get X equal to 31. Actually, what it is minimizing? It is minimizing total citizen miles squared value S rather than total citizen miles. So if you take the graph, it comes like this. So practical center of gravity method, if it is 0, 1, it is 31. If it is 50, it is 50, 100, 69, and 31, 43. And the center of gravity method by physics center of gravity method shows that optimum is somewhere at 31. So what is the inference? Physics center of gravity is good for balancing a tray or a plane, but not suitable for supply chain network design. Hope this is clear. Let us take a simple city problem, 4-city problem. We have the demand. Now I am doing a little bit of calculations. So demand at A is 15, demand at B is 20, C is 30, and D equal to 10. And distances are shown. Coordinates are given, so you can easily find out the distance. Now, from Pythagoras theorem, you can calculate this distance also, so 7.07. Now, if I locate the warehouse somewhere here, so from warehouse, it will be distributed. So average weighted demand distance. So I multiply demand by distance, since the distance is 7.01 for all the locations of the customers. So it comes to 7.07. But if I want to locate it a center of gravity method, so I will have to find out the coordinate of the center of gravity. So how do I find out the coordinate of the center of gravity? So I'll have to use this formula. So sigma demand into X coordinates, then sum it up, and then demand into Y coordinates and sum them up, divided by total demand 75. So it gives this. So if you go back to this, so this is the coordinate of this location of the warehouse. So by applying Pythagoras theorem, we can get this, and average weighted demand distance comes out to be 6.98. So I'm taking the two distance now and finding out the average weighted demand distance, it comes to 6.98. But suppose I go for practical center of gravity location, I locate it at a maximum demand point, so let's say 30, that is at C. Now here what is happening, I can calculate the demand distance between A and C, so that comes to 14.14. I use this formula and I find same formula and I find 6.82. So by using practical method, I was able to get average distance is 6.82. So the comparative chart, you can see average weighted distance is 7.07, 6.98, and 6.82. But if I want to find out the percentage of demand within 0 kilometer or within 6 kilometers, within 0 kilometer, it is 40. So up to 5.9 kilometers, this scores over another. So this chart gives you a lot of insights into the problem, how best I can serve the customers and how can I minimize the distance. So we found out, we're coming back to the same problem. We used capital at 5, then went for capital at 16, and went for capital at 11. And we found, and we made a comparative chart of the percentage of population within 100, 200, and 300 miles for different locations of the capital. And what we see actually, This average distance miles COG is 388, but whereas somewhere 370, this is little less, and these are little more. So you can get a lot of insights into the problem and take the best decisions looking at it. So inference, cities 4 and 10 are very interesting. These are farther away from physics or mathematical center. Both have 4% population. City 10 dominates the percentage within 200 and 300 miles. City 10 happens to be very close to vast majority. So observations, comparing candidate locations allows the planners to exploit the richness of the problem. More realistic and practical formulation of the problem is solved by linear and integer programming, which we are coming now. And the technique used ensure minimization of weighted average distance and picks the locations we can use. So real life distribution problem. Now we'll come to the problem. Basically, we want to use P facility locations out of so many locations we have decided. This is an athletic company, and most supply network design modeling will begin with a set of potential facility locations from which to determine the optimal. So suppose we have demand points, St. Louis 9 city. So all the names of the cities are given here, and the formulation will be like this. Now it's a little bit complicated, but so we earlier said that there must be an objective function. So this is the objective functions. These are the constraints. These are the constraints. And these are the binary variables. That means the two variables Yij. That means Yij, you know that it indicates that actually material flows from warehouses, this one, to customers. Now, if the warehouse I to customer J in a set of J, capital J, and here I belongs to a set of I. That means W may be W1, W2, W3, W4, W5, and customer may be J1, 2, 3, 4, 5, 6. So like that, it has got a set. Both have got sets. Now these are binary variables. Yij is either 0 or 1. That means there will be a flow from I to J. That means if I choose I equal to 1 and J is 3. So 1 to 3 will be there if its value is 1. If it is not there, its value will be 0. Similarly, Xi means the plant will be open or warehouse will be open. It will be 1. If it is closed, it will be 0. And Xi is greater than Yij because I cannot keep a plant open. Suppose plant is not open, so Xi will be 0. And Yij should also be 0. It cannot have a value of, this Yij cannot have a value of 1 because Xi is 0. So it is like this, and sigma Yij equal to 1. That means I'll deliver the full quantity to my customers from one warehouse. Generally, the customers would like to have one supplier of their material. They cannot afford the same product. So it removes a lot of hassles and difficulties during operations. So that is the reason customers always want a single product, one product from one warehouse. So this is the distance matrix with those data I was talking of. So the distances are there: 720 miles, 790 miles, 996. And when I do it in a solver engine, this I have solved in solver, Excel solver. And if I chose 4 cities, I can choose 3 cities also. If I choose 3 cities, I these are the three cities, the most optimum cities. So Chicago, New York, and Charlotte. Whereas if I open four warehouses, I should open Chicago, New York, Detroit, and Charlotte. So, but the now when you look at the Y, if I look at the YIJ chart, sorry. If I look at the YIJ chart, that means Chicago will deliver to Chicago. Definitely the distance is 0. It is supplied to St. Louis. New York will supply, this is the New York, will supply to Boston, and Detroit will supply to Detroit, Cincinnati, Pittsburgh, and Charlotte will be like this. Similarly, I can get an YIJ chart for 3 cities. But the ultimately average weighted distance has increased by 19 miles. That means if I go for 3 warehouses, then average personal mile distance will be 56 instead of 37. So I'll have to sacrifice in distance, but cost-wise, I'll save some money. So this is the I've shown here. So for 3, this 1, 2, and 3. And 1 is distributing to these 3 centers, 3 demand points, 2 is distributing to Pittsburgh, and this one Boston, and this one Charlotte will deliver to this is I think Atlanta. So you can take now a bigger problem with 200 cities. Now if you distribute through 4, it will look like this. So you will have a combination of 25 C4 combination. You must remember that you are choosing 4 out of 25 possible locations. So that's why the computer will do this calculations and find out the optimal values. If you do it for 9 locations, it will look like this. So as you increase the number of facilities, you are reducing the weighted average distance, but at the same time, your cost is also going up. You can see the comparative chart. Now, suppose, for example, 4, if I take 4 warehouses, so 31% of the demand you are able to meet. So you are able to meet 31%, you are able to use 100, then 100 to 400, 38, and 400 to 800, 24%, and for 800 to 32007%. But weighted average distance is 311, but you can reduce the weighted average distance, but beyond 4, I'll say that this gain is not much. In fact, I'll say from 3 or 3rd onwards, the gain is not much. So you make a choice that which one will go for. You will go for. Now, so long we have formulated the problem with distance. Now, if I substitute distance in the previous problem formulation by transportation cost per unit, this is the transportation cost per unit, this is the demand, and this is the decision variable or binary variable. Now, if you replace demand a distance figure by transportation cost figure per unit, then you are minimizing the total cost. That means the minimizing the distance, demand distance, virtually you can utilize it for minimizing your cost. Rest of the things are all same. You are limiting the number of facilities with this constraint. And this already I have explained, and this I have already explained. So it remains the same. Now, if you use capacity constraints, then you will have another constraint like this. I have shown by capacity constraint, and here the two stages are there. And capacity of total capacity of all as a particular warehouse Xi must be more than volume which is going from that warehouse to the customers. So it's quite obvious it should be less than capacity. So any supply chain problem is a multi-objective optimization. So on one side, we are trying to minimize the weighted demand distance or cost, and another side, we are trying to maximize the amount of demand within a certain distance or service level. So if a solution has the multiple goal property as constrained in the second problem and solve the second one, so we can solve both the problems, but we'll take the solution for the first problem and make it a constant in the second problem and then solve the second problem. That means out of the two solutions, you cannot optimize both. So one you will have to sacrifice and the other one you will have to achieve. So that is how it's done. There are other powerful solutions also. The various goal programming techniques are there which are utilized. But for the time being, this is what is called Pareto optimum method. Now, this is, we have added the constraints for service level. That is what we are trying to maximize the demand within high service distance. That means high service distance, if it is 800, so we want maximum customers to be within 800 kilometers. All customers cannot be within 800 kilometers. So we are trying to maximize the number of customers. So it will be 800. And maximum distance we also specify is the 1200. And then we put some average distance. So all this can be put together in the formulation, and we find out from the first formulation what is the maximum distance or maximum service distance. High service demand distance, we can, and go to the second problem. As I said, it's a multi-objective problem. We can take this higher service demand from the first problem and make it a constant here and solve this problem. And then we'll get the minimize demand distance, or objective function is minimize demand distance or minimize cost. You can take both of them, any one of them. So you might have three echelon supply chains also. So instead of two stage, as I said earlier, I to J, but here you have a plant in between, a plant at the end, and it may be like this also. And the formulation takes a little different shape. And here, from here, you can see these are the plants which goes to warehouses, and from warehouses it goes to the customers. So there are three stages. So three stages, and the formulation is a little bit complicated, but we have brought one for your information. We have brought one new variable by ZLI, which means from the plant to I. So what is the actual flow? So that is it varies. Its value is greater than equal to 0. From the bottom you will find that this shows the actual flow of materials from the plant to I, and then from there the old formulation which I've used remains the same. But here one more thing we have introduced, that P mean and P max. So number of facilities, the lower limit and the upper limit we have also fixed up. So there may be problems like this multi-site production sourcing and multi-product also must be there. So you can go on building up your supply chains accordingly. These are some of the other another consumer products company. And once you design your supply chain, you must work it in operation through simulation. So I strongly suggest that all of you who are in the network design or going to be in the network design in future, please remember that unless you check it on with simulation, it will be a futile exercise. Here, a lot of uncertainties has been incorporated in the simulation models. Got SCM Globe, or there may be other softwares are available, Analytica or Arena also is there. So you can utilize any of the softwares and check your supply chain whether it's operating successfully or not. You must remember any supply chain will your product will move seamlessly across the supply chain if you ensure that efficiency of network design is very high. So that is very, very important. You must be capable of designing your network in such a way that if there is a disruption like this tsunami or COVID-19 or whatever it is, you can shift to some other suppliers and check it on simulation model. So what are the lessons we have learned from this? Physics center of gravity method for location of facilities for distribution is not feasible. We can find out single or more points related to the demand, and this is done by minimizing the average weighted distance. Pick the best ones out of all combinations, and this should be your building block for designing any supply chain network. Any supply chain problem, always remember it's a multi-objective one. So minimization of average distance, demand, or cost, maximization of the number of customers within high service level. So you cannot neglect the customers, and you must serve them well if your supply chain network design should be according to the data. Solve complicated supply chain problems by modifying objective functions and adding constraints for service level, capacity, fixed cost, stages, multiple products, etc. And using powerful optimizing tools. All optimizing tools are available. Ciplex, MATLAB, Mathematica, Excel solver. You can use Excel solver for small problems, R, etc. And acknowledgement. This is the first one. Is one of the best books I have ever seen so far. And Supply Chain Management by Chopra. And G. Srinivasan was my head of the department in IIT Madras. And I have got a lot of lectures from SCM, IIT Madras. Then I've given Global Link also, SCM Globe, as well as any logic. So write to me for any clarification at ravinath.bhattacharya@yahoo.com. So knowledge leads you to light, but remember, imagination lets you grow. Thank you very much for having the patience to listen to my lecture, and wish you all the best. And please stay safe. Thank you.